Well, thanks for the nice introduction, and thanks for organizers for organizing the QIP here. Well, actually, I started attending QIPs from the second one, but the first one had one very inspiring paper, and what I will be talking about is related to that paper. So when the first QIP happened, I was not yet working on quantum computing, but then I saw a list of abstracts, and I was very excited by paper Quantum Lower Bounds by Polynomials by Beals, Burman, and company. And what I'm talking today is related to that. Okay, so I'll be talking about quantum computing in the query model. So we have function of some number of variables, and these variables are given by a black box, which you can query for values of variables. And you measure the complexity of a quantum algorithm by the number of queries that it makes. So this has been very fruitful framework in quantum complexity, as you can model a pretty wide range of problems through it. And classically, a query algorithm looks like this. So you first ask a value of a variable, then depending on the answer, you may ask another variable, and depending on answer, you may ask yet another variable, and so on. And your complexity is the depth of this tree. And quantumly, typically, a query is a controlled phase flip transformation in which you flip a phase of a basis state if the corresponding variable is 1, and do nothing if a variable is 0. And then you do a sequence of transformations that consists of queries and other transformations, and you measure your complexity by the number of queries that you make. So all that matters is how many queries you make. And it's a simplification of a quantum computation in the sense that you disregard the complexity of transformations in between the queries, but it's a very useful simplification, as the number of queries is something that you can both upper bound by giving a quantum algorithm and lower bound by giving a quantum lower bound. And there are two main methods for proving lower bounds on quantum algorithms. One is adversary method, and the other is polynomials method, which was presented at the first QIP. And it appeared as an archive preprint about 2 months after the first QIP. And for these 2 months, I was waiting until it gets us out as an archive preprint so that I could read the paper. And polynomials method is based on a mathematically very simple observation that if you have an algorithm in the quantum query model, you can write the amplitudes of this algorithm as polynomials in the input variables. And the degree of these polynomials is at most the number of queries that you make. So amplitudes are polynomials of the same degree as the number of queries. And then if you look at the probabilities of various outcomes, probabilities are amplitudes squared, so they are polynomials of degree at most twice the number of queries. So what one gets is that if a function is computable in the query model with k quantum queries, with say probability at least 2/3, then there is a polynomial of degree at most twice the number of queries, with the following properties. If a function is 0, polynomial is between 0 and 1/3. If function is 1, it's between 2/3 and 1. And if function is undefined, this polynomial still has to be between 0 and 1. So this polynomial is the probability that the quantum algorithm outputs answer 1. And this has a consequence that you can prove a non-existence of a quantum query algorithm by proving non-existence of a polynomial with these properties. If you want to prove that Grover's search requires at least square root of n queries, you can do it by proving that there is no polynomial with degree at least square root of n over 2 that satisfies these properties. Okay, so now let me introduce the complexity measures that I'll be talking about. So there are 4 of them. There is the exact degree, which is the minimum degree of a polynomial that is exactly equal to a function. There is approximate degree, which is the minimum degree of a polynomial that is approximately equal to the function. And then there is exact and bounded error quantum query complexities, which are the number of queries needed to compute function either with no error or with error at most 1/3. And because of connection between quantum query complexity and polynomial degree, exact quantum query complexity is at least half of the exact degree. Bounded error quantum query complexity is at least half of the approximate degree. And this is one of ways how to prove quantum lower bounds on search. And it can also be used to prove lower bounds on number of queries for other problems like collision, element distinctness, or lower bounding complexity of exact algorithms. And in those cases, it's actually the easiest method how one could prove lower bounds on those problems. And if you have a total function, it's known that quantum query complexity is characterized by polynomial degree up to a polynomial factor. So if you have a polynomial representation of some degree, the quantum query complexity is at most cube of that degree. And if you have an approximate representation by polynomials, and quantum query complexity is at most 4th power of degree of this representation. So quantum query complexity is always between degree and either the 3rd or the 4th power of degree, depending on whether you consider exact or approximate polynomial representations. Okay, so now this all is about total functions. So for total functions are the functions which are defined for every possible combination of input variables. And if you have a total function, it means that for every combination of input variables, a quantum algorithm must output a definite answer. It must either output an answer 0 with probability at least 2/3 or 1 with probability 2/3. So there should be a sharp boundary between cases where quantum algorithm outputs 0 with probability 2/3 and 1 with probability 2/3. And in that case, we can use the existence of this boundary to show that quantum complexity is polynomially related to degree and to several other combinatorial complexity measures of functions. And then quantum speedups are at most polynomial because the classical query complexity is also polynomially related to the same measures. So it's Grover's world, in which speedups are at most polynomial. And then if we go from total functions to partial, then things change. And things change because there are inputs on which function is undefined. A quantum algorithm is free to output an inconclusive answer on those inputs. That gives a lot more possibilities to quantum algorithms. And here, big quantum speedups become possible. There is a correlation function on which we worked with Scott Aronson, for which there is a quantum algorithm that solves it with one query. But classically, you need a number of queries that grows with the number of variables. And there are other examples of either unbounded or exponential speedups here, a lot of them. So the question of this talk is, how does quantum query complexity relate to polynomial degree for partial functions? And this has been essentially open. The biggest speedups are the same, the biggest gaps are the same ones as for total functions. And today I will show that there are actually functions that exhibit big gaps between these measures. So if we look at functions of non-Boolean variables, there is a function with polynomial degree 9, fixed polynomial degree, and quantum query complexity that grows with the number of variables. So it's an unbounded gap between degree and quantum query complexity. And for Boolean variables, there is an example of a function with logarithmic polynomial degree and quantum query complexity that is n to power 1/3. So that's an exponential gap between these two measures. So this polynomial relation between degree and quantum complexity that was there for total functions, it breaks down here. Okay, so now let me briefly sketch how this function looks like. And I'll do that by showing a candidate function, a candidate problem that we considered before coming up with the right problem. So the right problem is a bit more complicated, but I'll start with a simpler candidate function that we considered. So the starting point is Simon's problem. So this is the first example of an exponential quantum speedup. We have 2 to the n variables that are indexed by n-bit strings, and we have to distinguish the case when all these variables have different values from the case that there is some hidden string with the property that adding this hidden string to an index of a variable always results in another variable having the same value. And this is a problem that can be solved quantumly with just logarithmic number of queries. But it requires square root of n queries quantumly, classically. So this is the exponential quantum speedup that preceded Shor. And what this is distinguishing a case when this array of variables xi is 1 to 1 from the case when it's 2 to 1, but with a very specific type of 2 to 1 pattern. Now, this thing that it's 2 to 1 with a pattern and not just 2 to 1 is important, because if we consider a problem of distinguishing whether an array of variables is 1 to 1 or 2 to 1, that's another well-known problem in query complexity, that's collision problem. And distinguishing a 1 to 1 array from 2 to 1 array takes n to 1/3 queries quantumly. And this is often shown as an example of how you need structure for exponential quantum speedups. If the question is determining if a function is 2 to 1 with some structure, that's an exponential quantum speedup. If it's determining whether it's just 2 to 1, it's polynomial speedup. So our initial idea was to interpolate between these two problems. And our initial idea is what I called scrambled Simon's problem. So we have exponentially many variables, and we have to distinguish the case that all variables are different from the case that these variables have been obtained by applying one of several permutations to variables that satisfy Simon's promise. So you have an instance of Simon's problem, and then you mix around these variables according to one of several patterns to make the problem harder. And then, on one end, you have Simon's problem in which you don't mix up variables at all. On the other hand, if you mix them up in a completely arbitrary fashion by using any permutation, you get collision problem. And then there are cases in the middle where you mix these variables up, but you mix them up by using one of a small set of permutations. So the question at which we looked at was how does the degree and quantum complexity increase in the middle? And for this particular problem, it actually turned out that they increase at the same speed. But then we came up with a more complicated example. So this is what we call the tripartite matching problem, in which we have three sets of variables, and the question is it true that the first variables from each set sum up to certain value, second variables to sum up to some other value, and so on? Or is it true that none of these equalities is true? And this is something that we can solve classically by querying three variables in one group, or quantumly by querying two variables in one group. And it also has a polynomial representation of degree 3. And now, if we take this problem and scramble it around a little bit by permuting variables in one of several ways, we can get a problem in which polynomial degree stays constant, but quantum query complexity increases a lot. So polynomial degree representation of this problem is not very much disturbed by scrambling this problem, but for quantum algorithms it becomes much harder. And then, well, let me say a few words about the methods. So this polynomial degree part is pretty much a direct construction of polynomial. Quantum lower bound is a bit complicated. So we have to use the negative weighted adversary method. So the version of the adversary method that is most commonly used is the positive adversary. For that method, it's actually known that it cannot give more than a polynomial gap between degree and quantum query complexity, even if function is partial. So we have to go to a negative weighted adversary method and do a quite complicated argument for which I find it hard to give intuition on one slide. And yeah, so let me conclude with a few open questions. So one big open question that has been open for many years is how does quantum query complexity relate to degree for partial functions that have to be defined on a large subset of inputs. So we know that the gap between these two complexity measures is at most polynomial for total functions. We know it can be exponential for partial functions if we allow these functions to be defined on relatively small subsets of inputs. The question is, what happens for partial functions that have to be defined on most inputs? A second interesting question is separating examples of natural functions for which query complexity and polynomial degree differ. That is, example of functions that are not invented to prove complexity separations, but would be naturals to study by themselves. So here, the only known example of such problem is surjectivity, which is the problem in which you have n variables, and the task is to determine if for every value in a certain set, there is a variable that is equal to it. So this problem has the property that quantum complexity is n and polynomial degree is n to 3/4. And I think that's the only example of a natural problem that shows gap between these complexity measures. For everything else, if there is a polynomial representation, there is also a quantum algorithm. And the last one, so we had this tripartite matching problem. Does the lower bound also work for the bipartite matching? It could work. We don't see a reason why not. So thanks.
Okay, thanks, Andreas, for the very interesting talk. So we take questions.
Hi, I have a question. So I don't understand why your first theorem could not apply to the second theorem.
Okay, which is my first theorem?
It's one of your first slides where you show like for the all the alphabet and the binary alphabet.
Okay, yes.
This one. So I don't understand why you could not take like q equals 2 in the first theorem and we get a better version of the second theorem.
Okay. Well, for the lower bound in first theorem, I need q to be at least some power of n. So the quantum lower bound in the first theorem only works if q is sufficiently large.
Okay, I see.
So
okay, it's not for any q. I see.
Yeah, it's not for any q.
Okay, good. Okay, thank you.
All right, other questions? Oh yeah, it's over there. Yeah.
Also related to this slide, so this separation that you give for Boolean functions, that the degree is logarithmic and the quantum query complexity is polynomial, do you think the degree could be, or the approximate degree or whatever, could be constant? Can you get constant versus polynomial?
Yeah, why not? I don't see a reason why not.
Thank you.
Thank you for the talk. To follow up on this question, what is the approximate degree of this function that you use to prove the separation, like for the Boolean function? Do you know?
Yeah, I don't know what is the, I don't know, but I don't expect it to be a constant. I think it's probably logarithmic, although I have not proven it.
Thank you.